Hello and welcome to the Daily Space for Monday, May 21. There's 230k miles to the moon. I've got a full slate of stories and a half cup of coffee. It's storming out and I'm wearing sunglasses. With all apologies to the Blues Brothers, I'm wearing sunglasses today due to a horrible allergic reaction that no one needs to see and I wish I hadn't seen. So the show must go on, allergic reactions or not, and I appreciate all of you showing up to get your quick roundup of today's news. So Mondays are often a big news day, but I think everyone's a little bit sleepy after all the space launches that took place this weekend. Some of them streamed, some of them not, some of them occurring at sunrise this morning. Now, not occurring at sunrise this morning, we have the Kwakian, and I know I mispronounced that. Please bear with me on my pronunciation in this story. The Kwakian relay satellite lifted off atop a long March 4C rocket from Kaicheng Satellite Launch Center in China just yesterday. Now that I could find, this wasn't streamed live, so I didn't stream it here on CosmoQuest. If there are launches at rational hours of the day, we're going to do everything we can to bring you those launches along with full commentary. So this particular mission is a start to China continuing its exploration of the moon. With this particular relay satellite, they're putting it in orbit on the back side of the moon, the side of the moon we never get to see and often misname the dark side of the moon. Now, all parts of the moon at various times get the exact same amount of sunlight. The catch is, because our moon is tidally locked to the Earth, we only ever see one side of it. But if you think about it, when we're seeing that full moon, it's because the sun is directly behind the Earth, sunlight is coming around the Earth, and the moon is above or below the Earth's shadow, getting totally covered in sunlight, the side that's facing us. But 15 or so days later, when that moon is around on the other side of the planet, we may not see it at all. And in fact, it's usually a 3 or 4 day crescent that we're able to see because the moon is going from having its position below or above the sun in the sky, having the back side of the moon completely illuminated. And it's only as it creeps around that we start to be able to get some of our side, that visible side with the old man in the moon, re-illuminated. Now with this particular satellite, what they're doing is they're putting it in an orbit that is gravitationally balanced with the Earth and the moon, allowing it to constantly stay on the dark side of the moon. Now this does mean that it's a bit tricky to get communications back to Earth, but we're working on figuring all these things out. And the reason this relay satellite is there is so that we can get information from the surface of the moon. If you think about it, sometimes you just need to have a few extra spatial friends. In this case, to make this entire system work, they're going to need to have a relay satellite to relay information from a lander and rover, Chang'e 4, that they hope to land on the moon in November or December. And we will be bringing you all the latest science from that as soon as we can. Now let's just think about this right now. The Chinese, whose space coverage we don't get very much of, just successfully launched a relay satellite to the far side of the moon in preparation for a lander and rover. This is going to be the first time that we've had this level of exploration of the backside of the moon. Now, while Kwakian is on its way over to its new location, it is traveling along with a couple of friends. As always, there was the need to send, well, CanSats, or in this case, microsatellites. Traveling along with Kwakian are two microsatellites called Longzhan 1 and Longzhan 2. These are going to be doing some radio astronomy research, working to figure out just how much science we can get out of these tiny satellites. And speaking of radio astronomy, the Kwakian satellite doesn't only have Chinese-made instrumentation on board. In fact, a group of Dutch scientists from a variety of institutions and companies have developed a radio dish that that they already have put and already launched with this satellite. This particular radio dish, once it's unfurled when they launch Chang'e in November or December, is going to be able to observe our night sky in colors of radio light that just don't get through our atmosphere. So, this launch, one of the reasons I haven't been showing you a lot of pictures is, whoa, that was not the correct thing. Let me move this sideways. Sorry, production fail at its best. This is the best photograph I was able to find. So the Chinese missions are kicking butt. They just don't have the same production values. But you know, I will take poor photographs of a successful mission over great photographs of a okay mission any day of the week. So with that satellite from the Netherlands that is flying on board this new relay satellite, we will be able to see colors of light in the radio between 10 gigahertz and 30 gigahertz that normally don't make it to the surface of our planet. These particular colors of light are blocked by our Earth's atmosphere, and unfortunately, they're also the exact colors of light that we want to study to understand star formation and other things that were occurring in the earliest days of our universe. So thanks to this Chinese mission, a group of Dutch satellites, again, once everything is turned on and unfurled in November or December, they're going to start sending us new and amazing information about how our universe went from being a thick with very few density differences, essentially cloud of atoms, to being this amazing structure we have today. Now, not all news is involving this particular launch. In other planetary news, we have discovered yet again an asteroid that appears to have been borrowed from a different solar system. Now, if you embiggen this video, you can just make out there's a yellow circle with a small object inside of it that appears to be moving against the background of stars. Now, this is an inverted image, so stars are in black, asteroid is in black, and the sky is, well, that fuzzy, noisy shade of whitish gray. Now, we're keeping the asteroid centered in these images, and you see the stars moving. Of course, you could keep the stars stationary and you'd see the asteroid moving against the stars. Now, the way we figured out that we think this particular asteroid, which has the name 514107, 2015 BZ509, in the great tradition of bad names for things, the reason that we have figured out that we think this particular asteroid comes from another solar system is it's orbiting out near Jupiter, but in entirely the wrong direction. So in news coming from the Royal Astronomical Society, we learn of a new study that was done using the Large Binocular Telescope, where scientists stared at this particular object and then ran computer models to try and figure out, based on its extraordinarily stable orbit, could it have gotten here through a series of interactions with other planets? And as near as those simulations, so this isn't based on observations yet, this is simulations. So based on these scientists' simulations, we now think that this asteroid, which is moving backwards in its orbit out near Jupiter, had to have gotten in to this backwards orbit, retrograde orbit, actually retrograde, not appearing retrograde, it's actually moving the wrong way around the solar system. We think the only way it could have gotten here is if we ruthlessly stole it in the early days of our solar system. Our solar system, like all solar systems, would have formed in a cloud of dust gas along with a myriad of other stars. When you look at the Orion star forming region, when you look at the Lupus star forming region down in the southern hemisphere, what you're looking at is a place where solar systems like our own future solar system are in the process of forming. And in these tight, crowded, crazy complex places, it's possible that we can essentially gravitationally rub up against another system and steal a rock like this one. Now, in order to determine, is this truly a visitor from another solar system, or as the authors of this press release put it, a permanent immigrant from another solar system. So this is a rock that has come here to live. In order to figure out if it's truly from another solar system, we'd have to be able to go visit it, take a sample, and analyze the contents of that sample in comparison with other asteroids in our own solar system that have formed at a variety of distances. The reason we have to do so many comparisons is things that formed at different distances from the sun have slightly different compositions, slightly different ratios of different isotopes. We can only prove that this didn't come from right here by showing that it's made of a ratio of atoms that otherwise is unique to our solar system. Who knows if this will ever happen, but for now it makes for an interesting and, dare I say, scientifically intriguing, and I want to go there and take a sample, story to keep an eye on. Now, to continue our theme of space rocks, the Cassini mission pointed out to us that a variety of the space rocks, or small moonlets that are orbiting around Saturn, happen to be shaped a bit like ravioli. And Martin Rubin at the University of Bern is a computer simulator, a person who writes computer simulations in their astronomy department, who got to looking at this and wondering, how on earth do you get a ravioli in space? And in trying to figure out how you make a ravioli in space, he went and talked to fellow University of Bern scientist Martin Jetzi. So we have Martin and Martin studying ravioli. And what they were able to determine is, it looks like these particular things came from collisions of small moonlets that occurred face on at just the right speeds with objects of just the right densities. So here you can see the results of their computer simulations. And by varying the impact angle, by varying other different situations in the collision, they were able to reproduce the various moonlets that we see out around Saturn. Now, here you can see our three different vaguely pasta-shaped moons, Pan, Atlas, and Prometheus. The top row of images is the actual Cassini images. The images in the bottom row, well, those came from computer simulations. So when we get our computer simulations to match reality this well, it's time to celebrate and say, hey, we finally know how Cassini is making ravioli. Now, I was intending to do, now that I've finished our roundup of today's big stories, a summary of the latest results coming out of Gaia's data release 2. However, due to the rather horrible allergic reaction that has me resembling one of the Blues Brothers, I'm instead going to postpone that until next Monday, which means we'll have even more results from Gaia to discuss. For now, I am going to answer your questions, and for those of you who tuned in late, my name is Dr. Pamela Gay, and this show is here to bring you a quick roundup of all that is new in space and astronomy. If you like what you see, go ahead and give us a follow. Follows are free. Now, if you want to sustain the show and make sure that it keeps going far into the future, well, drop us a subscription, drop us a donation. Every little bit matters. This is a production of CosmoQuest, which is created out of the Astronomical Society of the Pacific. We are a 501c3 nonprofit that is dedicated to science literacy, which basically means we're here to put science in your brain. So I'm now going to pull up the chat, and if you can just at me with any questions you may have, it'll make it a whole lot easier for me to find those questions. Oh, you missed most of topic 1 as the mic was too low. Oh man, I must have a loose cable again. Thank you, Denizen of Earth. So the broadcast schedule on this is we are going to be on at 1 p.m. Eastern, which is 6 p.m. London, and mouthing is hard, 10 a.m. Pacific, Monday through Friday. So you can look for us 5 days a week. And if I'm not hosting, one of the other PhD researchers from our research team will be here giving you hopefully an equally exciting roundup of the news. Is this a bit better? I'm sorry for the audio problems. I seem to have a slightly loose cable in my setup that I need to work on fixing. So going back to the news that you didn't get quite as well as you wanted due to the plague of audio. Thank you, AstroWise. Due to the plague of audio issues. Let me see if I can adjust there. Whoa, is this better? That should be better. Okay, I think that's the best I can do without blasting you. So let me know if that works. Oh, I'm so sorry for the audio problems, everyone. Again, thank you, Denizen of Earth. Thank you, AstroWise. You guys are awesome. So to go back to this story, the Chinese launched the Kaon, and I don't know how to actually pronounce this, relay satellite. And we didn't have live video of it, or I would have streamed it to you. This launched yesterday from China, carrying a Dutch radio antenna with it. This particular relay satellite is going to the backside of the moon, where once the Chang'e 4 lander and rover arrives on the moon in November or December, it's going to be sending us back all sorts of amazing information. The particular Dutch radio telescope that is on board is tuned to look at radio wavelengths that we can't detect here at the surface of the planet due to our atmosphere blocking those colors. Yes, this was the Chinese launch. Oh, I'm so sorry that I blasted things. I'm sorry. Okay. So the reason I say backside of the moon is because, I can do this with, I got this as a souvenir when I was in China. It was the only thing I could find that I knew for certain I couldn't buy somewhere in the United States. So here is my moon. You, my camera friends, are the sun. And what can I use as the Earth? I think I have a bowl of planets. I do. Okay, I have a completely blue world that is not meant to be the Earth. Actually, let's see if I have something that isn't completely blue that I can grab out. Nope. Everyone should keep a bowl of planets in their desk. Unfortunately, I think I might have lost the planet Earth. Or it's at least at the very bottom of the bowl. Okay, I found Venus. I'm getting closer. Maybe this is Earth? No. That's Pluto. Because when I bought this bowl of planets, we thought that Pluto was a planet. Okay, I'm just going to go with Venus because I have no clue where I lost Earth to. So let's pretend this is Earth. And you, dear people out in camera land, and I'll embiggen the video. So let's imagine you are the sun. Now, my happy little strange critter. This is the moon. It looks very different on the front side and the back side. And the front side is all we see here at the planet Earth. Now, as my little guy goes around, he constantly keeps, coordination. He constantly keeps his little face pointed at the planet Earth. So right now he's getting the sun completely on his backside. Right now he's getting the sun on his side. Now he's getting the sun full on his face. But we only ever get to see his face. So since his backside can get completely drowned in sunlight, calling it the dark side of the moon, while a great reference to a great Pink Floyd record, isn't necessarily scientifically accurate. It's only dark in our understanding, and even that has changed thanks to the Lunar Reconnaissance Orbiter. So we need to, have a way to refer to the moon's other side, the side we never get to see. Rear side, back side, side we don't see, pick one, all of them work. Farron H., can you explain in more detail how and why tidal locking happens? Because it's not very intuitive. This is entirely true. I'm going to actually use a slightly different prop to do that. Okay, so here I have something that is clearly not circular. This is my mobile cam. And in fact, it always wants to rotate. Now, the reason it always wants to rotate is because its mass isn't distributed evenly. Now, here with strange, my friends say he is poop dude. My friends say this looks like they couldn't figure out why I bought it. So this little dude, he is not perfectly symmetric. So when he's going around his planet, if he tries to turn his eyeballs to look at the sun while he's over here, again, camera is the sun, the gravity of Earth is going to try and grab this extra mass and rotate it so that he always keeps his eyes on the Earth. Now, if he tries to keep rotating, he's going to get slowed down as the Earth tries to pull him back. Again, this is much easier to see with an object that's really, really not symmetric. It's torque. It's a lever arm issue. So when my camera is pointed straight at the Earth, this is gravitationally its best balanced position. Now, if it tries to rotate, the Earth is going to grab whichever one of these lever arms has more mass in it, and it's going to torque it back. And it's that torque that constantly occurs to a non-spherical object. This only works with a non-spherical object. It's that constant torquing that causes the object to get tidally locked. So if our little moon dude was actually a perfect sphere, no mountains, no canyons, density profile through the insides completely symmetric, the moon would keep rotating forever. But because our actual moon has its dense core off-center and its surface certainly isn't perfectly smooth, this allows the Earth to torque the moon so that it's constantly looking straight at us. Now, this wasn't an instantaneous process. It took a long time for the moon to become totally tidally locked to our planet, but this is where we are today. So I hope that explanation made sense. So Peter's saying, we know more about the moon now than we do about the bottom of the oceans. Yeah, that is unfortunately entirely true. This was especially pointed out during some of the search and rescue missions that have happened looking for lost submarines and lost aircraft. It is much harder to overcome the extreme pressures that exist deep under the ocean than it is to overcome the vacuum of outer space. with the vacuum of outer space, we just need to build spacecraft that are capable of holding in 1 atmosphere of pressure. When we go to the bottom of the ocean, we have to build submarines capable of holding out many, many, many times the pressure at the surface of the planet. So that difficulty in building robust explorers for under the ocean is part of why we just don't have as much data. The other problem is, with the moon, we can put Lunar Reconnaissance Orbiter in orbit, and as it goes around and around and around, it can take images of large swaths of the surface of the moon all at once. With an undersea explorer, well, you can sort of do that, but not with as big an area with sonar, where you bounce waves of sound off the bottom of the ocean, or with other kinds of remote sensors that aren't imaging sensors. But you're still limited in just how far through the water those waves will travel and then return to your detector. When you're deep underwater, you don't have light. So we can't stick something under the ocean that can take images a mile wide like we can when we stick something in orbit around the moon. So the lack of sunlight at the bottom of the ocean just means we have to basically image an area the size of this room at a time. And it takes a while to do that. The Earth is big, the oceans are varied, and you have to steer around mountains. Oh man, I'm running into problems because these lenses are prescription for distance, and I'm trying to read my screen with them. Cool. So I see Fen, I can't read the rest of your name, is saying cool. So total locking works only on uneven masses. Yes, that is entirely true. You got it. But now that the moon lost angular momentum, where did that energy go? So it turns out our moon used to orbit much, much closer to the Earth. Our Earth also used to rotate much, much faster. Days used to be under 20 hours in length, which is kind of awesome to think about. As the moon went from happily rotating to locked, it moved away. It lost angular momentum and moved away. Now, the moon is actually continuing to move further away because the Earth is ever so slowly trying to get tidally locked to the moon as well, such that, well, this ball has some writing on it. So imagine a future where the Earth always rotates to keep the same part of the Earth directed at the moon. So as our own Earth's rotation very gradually slows due to the exact same kinds of tidal forces, the moon continues to move further and further away. This is actually kind of interesting to think about in the contexts of solar eclipses. When solar eclipses occur, it's because our moon is at the exact right distance to completely block, to completely block the sun from getting its light rays to that part of the Earth. This particular alignment, I'm going the wrong direction. I don't know how to do this. Okay, so if I can't simulate this with my hands in the camera, if the moon continues to migrate further and further away from the Earth, it will appear smaller in the sky. And someday in the future, we will only get annular solar eclipses where we have a donut of sun because the moon is so far away it can no longer block the entire disk of the sun. So Larry is asking, what's the ultimate fate of the moon? Well, the moon, like many different things, is eventually going to get blasted by our suns expanding into a new phase. In somewhere between 5 and 6 billion years from now, our sun is going to run out of hydrogen fuel in its core. And when this occurs, it's first of all only going to have helium in its core, and second of all, it's not going to be giving off enough light pressure to support the outer atmosphere of the sun. Now, our sun isn't going to go supernova, nothing dangerous like that is going to happen, but it is going to collapse in a little bit. And at a certain point, it's going to collapse in just enough to ignite a shell of hydrogen around that helium core. And that shell of helium is going to burn at sufficient energy levels that its light pressure pushing outwards is going to overexpand the outside layers of the sun, such that our sun eats Mercury, eats Venus, and gets, well, its surface is going to get uncomfortably close to our own planet Earth. At this time, we're still going to have our moon. We're probably not going to still have a livable planet, but Earth will be here. And the moon will continue orbiting the Earth, as near as we know, till the fullness of time. So I see Larry saying, question, if it is possible to terraform Venus, what is your opinion would be the best way to start? Oh man, the best way to start. I personally would choose to start with Mars. So with Mars, you have a problem of not having sufficient atmosphere, and you're never going to have sufficient atmosphere, but you might be able to change the atmosphere enough over time to at least make things like different lichens, different high altitude grasses, capable of growing in deep valleys on Mars. With Venus, you kind of have things like hydrochloric acid falling out of the sky. So chemists, and as an astronomer, I am not a chemist, and I in fact managed to convince my university to let me take stellar nucleosynthesis in stars instead of second semester freshman chemistry. So me and my lack of chemistry would go find a chemist and try and find out, is there any way to seed the atmosphere of Venus with something that would change its chemical constituents to be something that is significantly more transparent to light, allowing heat to escape, allowing infrared radiation to escape through the atmosphere, ending the greenhouse gases, and hopefully changing the chemical layout of the atmosphere. I don't know if it's possible. I think the best hope would be that chemist, which I am not, says, well, yes, you use this and this. And then we happen to identify like a comet flying by that has a great deal of whatever those things are in it, and we direct that comet to Venus. But unless it turns out to be just as simple as bombarding Venus with comets and icy things, I don't know how we could do it. I just don't. There are people out there who've probably thought a lot more about this and have better ideas. So Denizen of Earth is asking, when the swelling occurs, does the sun's outer layer get continually less dense? Yes. In fact, our sun will become much less dense. It will also become much cooler, much redder. And this means that we're going to have a star that, because it has a significantly larger surface area, is going to be giving off more photons. But those photons, those pieces of light that it's giving off, are going to be of a much lower temperature. So we're going to have a brighter and cooler and less dense star in our solar system. So are there any more questions out there? I see one person is making a comment that Mars has polar ice caps. Yes, those can be useful. But yes, it does have an atmosphere. It just doesn't have an atmosphere that's useful. And it does have polar ice caps. They're not like ours. They actually have things like carbon monoxide and carbon dioxide in them, so dry ice. It's different. Any other questions out there, folks? If not, I'm going to go take more Benadryl for my rather horrible allergic reaction, which is why I'm wearing sunglasses. And hopefully tomorrow I will be back with full eyeballs to bring you tomorrow's news. Now, to give you a quick roundup of some of the things going on here on CosmoQuest X on Twitch, we are going to be bringing you Monday through Friday these daily rounds up on the news. On Wednesdays and Fridays, following the news, we are going going to have Matt Richardson working on various research projects to help us understand the moon using your citizen science data that you can add to our data set over at CosmoQuest.org. So if you want to help us explore our solar system, if you want to help us map out the moon, Mars, Mercury, Vesta in greater detail than we've ever been able to map them out before, click on over to CosmoQuest.org. Now, in addition to that, we have Tuesday nights. I come on and I'm working on some simple visualizations to explain different phenomena that we have the opportunity to observe. So join me at 9 p.m. Eastern, 6 p.m. Pacific, 11 a.m. Friday in Sydney, and I will bring you some programming. Now, Thursdays, we kind of have alternating projects. This week, we will be showcasing new lessons on how to do data reduction if you want to get science out of your CCD. And Thursday evening, again, at that 9 p.m. Eastern slot, I'm going to be bringing you an interview with a special guest who I don't remember at this moment, but stay tuned and we will bring you all the science and help you put it in your brain. So thank you all so much for joining me. Thank you, mods, for keeping things friendly and awesome and adding so much information to the chat. And thank you so much, all of you, for listening. Again, if you like what you see, give us a follow. Follows are free. If you want to sustain this show, give us a subscription, and every bit helps. This is The Daily Space, a production of CosmoQuest, which is part of the Astronomical Society of the Pacific. Wherever you are in the world, go out and have a great morning, evening, or afternoon. And remember to look up. Bye-bye.